Have you ever stopped and wondered what a computer actually sees when it looks at a photo? I mean, it doesn't see colors or shapes the way we do. It sees something way more fundamental. Today, we're going to peel back the curtain on image processing and show you the simple, almost elegant math that lets a machine make sense of our visual world.
All right, let's jump right in with a little puzzle. On the left, you've got this beautiful, vibrant photo of a butterfly. And on the right, a computer has somehow traced its outline perfectly. How does that even happen? How do you teach a lump of silicone to find the delicate edges of a butterfly's wing? You know, it seems like magic, but by the end of this, you'll realize it's something so much cooler. It's just math. So to crack that butterfly puzzle, we have to start at the beginning. We need to understand what a computer is looking at when it sees any image at all. Because before it can find a wing or an edge, it has to translate what we see into a language it can actually understand. So what is that language? And here it is. This is the secret. Honestly, this is the single most important thing to get your head around. While we see a beautiful sunset or a smiling face, a computer just sees a massive spreadsheet. Seriously, a structured, orderly grid of numbers. That's it. Every single thing you see in a photo gets boiled down to numerical data that a machine can finally process.
Okay, so an image is a grid of numbers. We've got that part. But what do those numbers actually mean? And how are they organized? To figure that out, we have to zoom way in and look at the fundamental building blocks of pretty much every digital picture you have ever seen in your life.
And it all starts right here with the humble pixel. You know, the word itself is just a mashup of picture element, and that's literally what it is, the absolute tiniest dot of color in a digital image. You can think of it as the atom of our digital visual world.
Now, take this photo of a zebra. To us, it's one image, right? But to a computer, it's actually just millions of those little pixel atoms all arranged in a perfect grid. Every stripe, every whisker, it's just a collection of these dots in a specific number of rows and columns. For perspective, a standard HD image is a grid of almost 2,000 columns by over 1,000 rows. That's a lot of dots.
This slide right here, this is where it all clicks. On the left, you see a grayscale image of the number 8. On the right, you see what the computer sees. For a simple black and white or grayscale image, each pixel just gets one number, usually somewhere between 0 and 255. 0 means pure black, 255 means pure white, and everything in between is just a shade of gray. The shape that we recognize as an 8 is just a pattern hiding in the numbers.
And what about color? Well, it's the exact same idea, just 3 times over. A color picture is basically made of 3 of these grids, all stacked on top of each other. There's one grid for how much red is in each pixel, one for green, and one for blue. So every single pixel gets 3 numbers, which then all blend together to create the final color we see.
Okay, so if an image is nothing but numbers, how in the world do we edit it? How do you blur it or sharpen it or find the edges of that butterfly? Well, we do it by changing the numbers. And we use this incredibly powerful tool called a filter or sometimes a kernel. And these things aren't just for fun photo effects. They are the absolute foundation of how machines learn to see.
So an image kernel is really just another grid of numbers, but a much, much smaller one. I like to think of it as a tiny magnifying glass that has a secret mathematical formula etched into it. To apply an effect, the computer just slides this little kernel over every single pixel of the big image one by one.
That is the million-dollar question, isn't it? How can this little matrix have so much power over a giant image? Well, the answer is a mathematical process with a kind of fancy name, but a surprisingly simple idea behind it.
The process is called convolution, and this diagram shows it perfectly. See how the small filter, the kernel, is placed over a little patch of the main image? The computer then multiplies each number in that little filter with the pixel number directly underneath it. Then it adds all those results together, and that one final sum becomes the value for a single brand new pixel in a new picture. Then the kernel just slides over one spot and does the whole thing again, building a completely new image, pixel by painstaking pixel.
All right, theory is great and all, but the best way to really get the power of convolution is just to see it happen. So let's do a quick fire round with a few classic filters and see what their simple grids of numbers can do to a real photograph.
Let's kick things off with the simplest one, the blur filter. Its kernel is basically just a little 3x3 grid, and it's filled with nothing but the number 1. Its whole job is to take the value of a pixel and average it out with all of its immediate neighbors. And here's what you get. By averaging out all those pixel values, all the sharp differences just get smoothed over. It creates that soft, kind of out-of-focus look. So simple, but it works perfectly.
Now let's do the exact opposite. Let's use a sharpen filter. The kernel for this one is designed to do the reverse. It has a big positive number in the middle to boost the original pixel's value, but it has negative numbers around the outside. This is a clever trick to dramatically increase the difference, the contrast, between a pixel and the ones right next to it.
And would you look at that? The details in the building suddenly get crisper, the lines are way more defined. It just makes all the important features pop right out at you. And it's all because of some clever math in that tiny little kernel.
And now for the grand finale, the edge detection filter. This is the one. This is what brings us all the way back to our butterfly. This kernel is specifically built to hunt for one thing and one thing only: big, sudden changes in pixel values.
So how does it pull this off? Well, when this filter slides over a spot with really high contrast, like where a dark pixel is right next to a bright one, like the edge of the building against the sky, it creates a bright white pixel in the new image. But in areas where all the colors are pretty similar, it just creates a dark pixel. And just like that, the filter basically ignores everything except for the outlines.
So I know what you might be thinking. This all feels a bit like old-school computer graphics, right? But believe it or not, these fundamental ideas are more important today than ever. Why? Because they are the literal building blocks of modern artificial intelligence.
And that's a fair question, right? I mean, we have these incredibly complex AI models that can generate amazing art and hold entire conversations. So are these simple, handmade filters still important? The answer is a resounding 100% yes. They are the bedrock that modern computer vision is built on.
Think about it like this. Modern AI, especially for computer vision, uses the exact same process of convolution we just talked about. The really big difference is that instead of us telling it to use a pre-made blur or sharpen filter, the AI learns its own filters. Through tons of training, it figures out the perfect little grids of numbers it needs to detect things like a horizontal line or a gentle curve, or even something as complex as a cat's ear or a car's wheel. It's all built on these same basic rules.
Which brings us right back where we started, to our butterfly. That transformation from this rich photograph to this clean outline, it's not a mystery anymore. It's not magic. It's just a computer, methodically sliding a tiny grid of numbers, an edge detection filter, across the image's own grid of numbers.
So the real takeaway here is that some incredibly complex behaviors, like sight, can actually come from a set of really simple, understandable rules. And that leaves us with one last huge question to think about. If these simple mathematical rules taught a computer how to see, what else can they be taught to understand? Thanks for joining me.